Please join me in giving me a warm town hall welcome to Eugenia Cheng.
Thank you very much, and thank you for that wonderful introduction. Thank you to the Town Hall Seattle for inviting me back to talk about this book. I had a wonderful time here when I came to talk about my previous book a couple of years ago. So thank you all for joining us to talk about infinity and what lies beyond infinity. Now, I was once called in to arbitrate a dispute between my 4-year-old nephew and his best friend about whether infinity was a number or not. His best friend said that infinity is not a number because my daddy says so, and my daddy's a scientist, so he knows everything. My nephew sensibly focused on proving that his daddy didn't know everything by reeling off Batman facts that his daddy didn't know. I love the fact that infinity is something children ask about and that adults can't answer. And for me, that's a wonderful place to explore what goes on in the world, what goes on in our minds, and to explore and nurture curiosity in children. And it's amazing and wonderful to me that it took mathematicians thousands of years to pin down a way of talking about infinity that would still make sense when you scrutinize it with logic. Now, unfortunately, there are many arguments in the world these days that do not make sense, even when you don't scrutinize them with logic. But certainly when you do scrutinize them with logic. And the whole point of math is to construct arguments that hold up under logic. And so that's what we're going to have a look at today. There are infinitely many things I could say about infinity. So I've had to pick some. And I'm going to talk about loops, paradoxes, the infinitely big. I'm going to touch on what infinity is, talk about dimensions, and finish by talking about the infinitely small. Loops are one of my favorite things, and they are how I think I first encountered infinity, because I grew up in a house that had a chimney, a chimney in the middle with a fireplace, and the idea was that all the other rooms went around the fireplace and were heated by the fireplace. And the thing is that my sister and I liked to chase each other around the fireplace, and because all the rooms were in a loop, we could basically chase each other infinitely far around the house. It was as if we had an infinite house. Of course, we could then also change direction and then have hysterics because we'd crash around the other side. But loops are a way we get access to infinity, even though our world is finite. And one of my favorite computer programs, in fact, my all-time favorite computer program, is one I wrote when I was 5. My mother taught me to program computers when I was 5, and I was very good at it, and I never got any better. So I still program like a 5-year-old. And the thing is that I was so entranced by my favorite program, I never got bored of it. And the thing is, I'm not easily bored, which has its downsides, because it means I never got any better at programming, because I could always do the same program over and over again, which is this. It was programmed in BASIC, which kind of dates me, but goes like this. 10, print hello. 20, go to 10. And then you hit run, and you get this. And I could do this over and over again, and I did do this over and over again, because now we have an infinite loop. And this was, I think, probably my first, along with chasing my sister around my house, was my first appearance of infinity in a loop. And what is infinity? Well, my friend Amaya Gabancho is a Basque translator, and she tells me that in Basque, infinity is the same word as 11, Jamaica, which kind of indicates that beyond 10, it might as well be infinity. And this idea is borne out by my friend Sally, who one day was counting, she was doing a stock of her jam, her homemade jam that she had, and she said, she posted this on Facebook, she had 3 jars from 2013, 10 from 2014, and lots from 2015. So somehow beyond 10 is lots. And in my work in higher dimensional category theory, in fact, higher means anything higher than 3. So in higher dimensional category theory, it goes 1, 2, 3, lots. And after 3, you might as well be doing infinity. So it depends what you like about numbers and what situation you're in, what counts as big. Another way we can get loops is if we sing around. And we probably all know this one, so I'd like to see if we can sing it all together. Now maybe if we start over here, everyone over here can go first, and then everyone over here can go second, and everyone over here can go third, and everyone over here can go fourth, and we'll see how we do. Okay, let's start about here. Row, row, row. Ready? Okay, ready. And row, row, row your boat. 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 Hooray! Now we could go on forever. There was one incident involving my nephew again, when my sister and I were walking him home in the pushchair, and it was raining, and he was screaming. And the only thing that stopped him screaming was if we sang "Row, row, row your boat" in a round and didn't stop. So we just kept going like that. And now here is my depiction of what we just did. So if you sing "Row, row, row your boat," then the next people start here, and the next people start here, and the next people start here. But I'm happy that you spontaneously carried on and you didn't just stop at the end, which means that when you got to the end, which is here, you started again. And the yellow people also started again. And the green people started again. Ooh. And the orange people also started again. And then we just kind of kept going. So we made this loop. And if you look at the 4 lines that are in each section, they're the same 4, they just rotate around the 4 groups of people. And so this loop is the infinite loop of row, row, row your boat. And we could keep going on forever because it's a loop and we can go around it as many times as we like. So this is another way we get to access infinity. Let's put that there now. I'm going to talk about some paradoxes now, because if we think about what infinity is and we're not careful about it, we run into some issues. And the issues, there are 2 things you can do when you run into a problem. You can either run away from it, or you can go, something looks interesting here. I think I'll investigate why this paradox seems to be happening. And if you're a mathematician, then what you tend to do is investigate why that paradox is there, rather than running away from it. So here's one that I really like, which is called Hilbert's Hotel. And you imagine in your head that you have an infinite hotel. So your infinite hotel has rooms 1, 2, 3, 4, 5, 6, 7, 8, and all the way on forever. This is, of course, not possible in real life. But the great thing about math is that it's not real life. So some people think that's a terrible thing about it. But I like it because it means you can do things that aren't actually possible in real life. In real life, there are all sorts of restrictions like time and money and physical stuff. Whereas in math, the only restriction is logic. And so you can do things like have an infinite hotel and then see what happens. So you can have a full hotel and then see what happens when one new guest arrives. And then you go, well, how about I just move the person in room 2 with room 1 into room 2, and I move the person in room 2 into room 3, and the person in room 3 to room 4, and so on. And they never run out of rooms to move into because it goes on forever. And that means that room 1 is now empty, and I can put the extra person in room 1. So this is something you can't do in a finite hotel. But it would have kind of changed the nativity story, wouldn't it? Anyway, Zeno's paradoxes. Hilbert's paradox was only from a couple of 100 years ago. Zeno's ones go back more than 2,000 years. And they're about motion and how we understand motion. So one of them says that Achilles can never beat the tortoise in a race. Achilles is very fast, right? But the tortoise says, I'm going to challenge you to a race. I just want a head start, a little head start. Not too big. And so then the point is that by the time, supposing the tortoise starts at this black line here, then by the time Achilles has arrived at this black line, the tortoise has gone forward a little bit. And then maybe the tortoise has got to there. And then by the time Achilles has got to there, the tortoise has got somewhere further. And then by the time Achilles has got there, the tortoise has got somewhere further. So that means that the tortoise is always going to be ahead of Achilles, right? Achilles is never going to beat the tortoise. But that doesn't seem quite right, because probably the tortoise is going to be beaten by Achilles. There's a wonderful video on YouTube, which you may have seen, where there's an actual race with a bunny against a tortoise. And it's perfect, because the bunny goes, ding, 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 and the tortoise is going, no, no, no. And then the bunny kind of goes, oh, I wonder what's over there. Oh, who's that? And then eventually everyone's screaming at the bunny to try and go that way, and the bunny never does. He keeps going on like this, and the tortoise eventually wins. It's brilliant. I love it. So the next paradox says that you can't eat all your chocolate cake because you eat half of it, and then you have to eat half of what's left, and then you eat half of what's left, and then you eat half of what's left, and so on, and there'll always be a bit left. There'll always be half of what's left. So you'll never finish your chocolate cake. And yet, I do finish my chocolate cake. And the last one is that nothing is moving. Because if you take a photo if we all wave around and someone takes a photo, in the photo, no one will be moving. Because it only captures one instant, and in that instant, no one is moving. So how is it that we're moving? And these are things that where some form of logic has violated what we understand about the world, and some people say that means that math is dumb. And other people say, oh, we should explore math further to see how we can resolve this using logic. And I'll get to some of that later. Here's the solution to all of this came 2,000 years later, and that's what calculus is all about. You might think that calculus is the thing invented to torture people in school. A lot of people say to me, oh, I was okay with math until calculus. Some other people say I was okay with math until times tables. I have sympathy with both of those things. But calculus is there to deal with infinity and the infinitesimally small things. And so although you may think that infinity is far away from this world, actually considering infinity and sorting out how to think about it is what led to the development of calculus, which controls everything that moves continuously in the world around us. So everything that uses electricity, everything in the room, anything that's got a curve in it, the curve of the piano, the way that the strings work, everything is controlled by calculus. So without that understanding of infinity, we wouldn't have any of these technological developments. So that's kind of a use for infinity. I'm a bit wary of talking about how useful math is because I don't like to think that that's its big selling point. It would be like saying that I'd like you to meet my friend. They're very useful. So math is useful, but often what motivates us to do it is the fact that it's fascinating, not the fact that it's useful. It's great that it's useful as well. Here's a picture of me eating Zeno's cookies. I made some chocolate chip cookie dough, and this first cookie is actually 1/10 of the whole dough. And then the next one is 1/10 of what's left. And the next one is 1/10 of what's left, and so on. The end ones I've eaten, they're going into my mouth. So now I'll talk about infinitely big things a little bit. What is infinity? Is it a number? Well, let's think about some big numbers. What does a million look like? I was thinking about this, and I was thinking I've probably never seen a million of anything. Well, there's a great book, a children's book called 1 Million Jelly Beans. Well, no, How Many Jelly Beans? And I don't want to do a spoiler, but I don't want to do a clickbait either. And the last page is a picture of 1 million jelly beans, and it's really cool because you have to unfold it because it's so big. But here's 10, and here's 100. Here's 10,000 dots. I couldn't make 1 million dots because my computer gave up, said you haven't got enough memory. It's because I have a kind of pathetic computer. But infinity is bigger than all numbers. It's bigger than how many people there are on Earth. And it's more than how many ants there are, or germs, or cells, or molecules, or atoms. We don't have an infinite number of things on Earth. But this doesn't tell us what infinity is. It only tells us what infinity isn't. Which would be like saying Yao Ming is taller than everyone you know. But that doesn't tell you who Yao Ming is. So what is infinity? Well, we can also think about where I said there aren't infinitely many things on Earth. But how about lines of symmetry on a circle? I was once helping some first graders with symmetry, and we did a triangle, and we did a square, and we did a hexagon, and so on. We did an octagon, and one of them said, this is a digression, but one of them said, an octagon has 8 sides because oct stands for octopus. So I eventually gave them a circle, and one of them drew this line, and one of them drew this line, and then one of them drew these lines, and then one of them drew these lines, and then one of them went, there's hundreds of them. And then the other one went, there's millions of them. And then the other one went, you could spend your whole life drawing them and you wouldn't finish. And then the other one just colored in the whole circle and said, I've drawn them all now. And I went home going, what just happened? I don't understand what just happened. But there are infinitely many lines of symmetry on a circle, so we do actually have infinitely many things, as long as they're not kind of physical things. So infinity is also a way of winning arguments, because someone might say, I'm right times 10, I'm right times 100, I'm right times 1,000,000, I'm right times infinity. But then what if someone else goes, I'm right times 2 infinity? Is that bigger? Is it bigger? Let's think about it. What happens if you think that infinity plus 1 equals infinity, because infinity is the biggest thing? Well, we could then subtract infinity from both sides of this equation, and we'd get 1 equals 0, which is not so great. We could then do infinity plus 2 equals infinity, and then we would get 2 equals 0. And if we keep going like this, we'll get everything equals 0. We could even suggest that 2 infinity is infinity plus infinity. If that's also infinity, and we subtract infinity from both sides of that, then we get infinity equals 0. Now everything equals 0. Now we're in the 0 world. That's okay. That's a perfectly valid mathematical world. It's just not the one that we live in. You can't do very much inside it. It's like the world of candy when I was little, because I was allergic to food coloring, so I couldn't ever have any candy. So no matter how much candy everyone gave me, I still had 0 candy. It's a very sad world to live in. So infinity is not an ordinary number. You can't manipulate it like, well, you can. This is the thing, in math, you can do anything. It's just that if you cause a contradiction, then you end up in the 0 world. So you can say infinity is an ordinary number, but only if you're in the 0 world. So what is it? It's not a real number. The real numbers are the ones that sit on this line. Here are the whole numbers, and in between them, there are all the real numbers. But maybe there's another kind of thing it is. And in fact, mathematicians have developed this, and it's called an ordinal or a cardinal number. And it's just the number of things there are in something. So you find some very well-defined, some kind of familiar set of objects, and you go, oh, it's like this. What's 10? This is 10. This is how we tell a child that what 10 is, right? It's the number of fingers we have. What's 5? This is 5. Then we go 5 add 5 is 10. And we can do infinity like that too. Infinity is how many numbers there are. We have to be a little bit careful about that. It's how many whole numbers there are. And the reason is that this is only the first infinity, because there are more infinities beyond that, because there are bigger sets than all the whole numbers. What on earth does that possibly mean? Well, let's think about this. The first infinity is how many guests fit in Hilbert's hotel. So remember that we could fit a new guest in like that, but that they still fit in the hotel. So that seems to be telling us that infinity plus 1 is still the same number of infinity, because we can still fit it in the same hotel. But it kind of depends. It depends whether you care about the hassle that you have caused infinitely many people. Imagine you've checked into a hotel and then they say, excuse me, you need to move room. It's kind of a hassle, right? So if you care about the hassle, 1 plus infinity is not the same as infinity plus 1. Because 1 plus infinity means one guest arrives first and then infinity guests. And in that case, you just put the first guest in room 1 and the infinity guests just start at room 2 and no one had to move. But infinity plus 1 means you put the infinity guests in first, and then a new guest arrives, at which point you have to move everyone up a room. So you've caused everybody hassle. So that's different. So if you're doing that kind of thing, then infinity plus 1 is bigger than infinity. And this is what I think Shakespeare knew. Because in The Taming of the Shrew, he said, if this be not that you look for, I have no more to say, but bid Bianca farewell forever and a day. Which he evidently thought was longer than forever. He didn't say a day and forever. Forever and a day is longer because you have to wait for the whole of forever and then another day after that. So there's a bigger infinity than the whole numbers. There's a bigger infinity than the number of people in Hilbert's hotel. And this is how many decimal numbers there are. So there are a lot of decimal numbers, and some of them go on forever. 1/3 goes on forever but repeats itself, so it kind of doesn't count. Whereas the square root of 2 goes on forever and never repeats itself, which is because it's what's called an irrational number, which means it's not a fraction. Whereas 1/3 is a fraction. Look, it's 1/3. So pi is another decimal number that's very famous that goes on forever and never repeats itself, so it's irrational. And if you count all of those ones, and you put them in with the rational ones, those are all the real numbers. And there are so many irrational numbers that there's actually more of them. Another way of saying that is if you had a Hilbert hotel where all the room numbers were decimal numbers that go on forever, don't think about how long it would take to ask for your key. But you wouldn't be able to evacuate that into a normal hotel if there was a fire. It wouldn't fit. There's no way of doing it. This was proved by Cantor. And what that's telling us is that there are more irrational numbers than rational numbers. And the irrational numbers, they're called, because it's a bigger infinity, it's called an uncountable infinity. Because counting is going 1, 2, 3, 4, 5. If you can count something, then you can put them in Hilbert's hotel. If you can't, because they don't fit, it's called uncountable. And by the way, there are also more irrational people than rational people. Now, there's quite a lot to take in, so I'd like to have a little musical interlude now. One of my favorite songs, The Infinite Shining Heavens, by Vaughan Williams, on a poem of Robert Louis Stevenson. I like to think that he knew about different infinities as well, because he says uncountable angel stars. So he clearly thinks that's the next order of infinity up from the whole numbers. So I will now let you ponder these things a little bit, and we'll think about the fact that infinity has inspired many people, including poets and musicians. Shining hands rose, and I saw in the night uncountable angel stars showering sorrow and light. I saw them distant as heaven, dumb and shining and dead, and the idle stars of the night were dearer to me than bread. Night after night in my sorrow, the stars looked over the sea, till lo, I looked in the dusk, and a star had come down to me. Thank you. I'm going to talk about dimensions now. Dimensions are one of my favorite things because I do higher dimensional category theory, which means I think in higher dimensions all the time. And I think actually we've all been thinking in infinite dimensions all our lives without necessarily realizing it. Just like Molière's bourgeois gentilhomme, who realized he'd been speaking in prose all his life without realizing it. So let's think about how many dimensions there are in the world. There are really only 3 dimensions in the world, or are there? Does 4-dimensional space exist? Well, Einstein made 4-dimensional space very famous with time, because one of his big insights was that if we count time as being a 4th dimension, then we get to understand how gravity works in a much better way. So space-time is a very famous 4-dimensional space. And you can think of it like this, that if you're going to meet up with somebody somewhere, then you need to tell them where in 3-dimensional space to meet up, but you also need to tell them when. Because if you go at a different time, you won't see them, because you're in a different spot in space-time. And another way to think about it is that to escape from 2-dimensional space, you need to use the 3rd dimension. So in order to climb onto this stage, which is escaping from the 2-dimensional space of the floor, I had to climb up some steps. Or if someone tried to hem me in with a fence, and if I could fly into the third dimension, I could escape. So if someone locked me in a cell, a whole room, I'd be enclosed in 3 dimensions, but I could escape by traveling in time. I could time travel to yesterday when I wasn't locked in the space. Then I could walk out of the space and come back to today, and I'd be fine. And there are plenty of fictional stories and books and movies where people do that. And I like that as a way of thinking about the 4th dimension. There's also music, which could be considered to be a 4th dimension because you sort of escape from where you are when you listen to music. And so if you're stuck on a cramped train with no air and you listen to music, then it takes you away from that and maybe you forget you're there. It's not clear if you've genuinely escaped, but it's a thought about what a 4th dimension could be. Then here is a 4-dimensional cube. So how is this a 4-dimensional cube? Well, let's think about a 3-dimensional cube for a second. A 3-dimensional cube is made by taking a pair of 2-dimensional squares and joining them up. So if we take a pair of 3-dimensional cubes and join them up, that's a 4-dimensional cube. And there are 4 pairs of parallel 3-dimensional faces on this cube. There's one pair. There's another pair of cubes inside it. Here's another pair of cubes inside it. And here is another pair of cubes inside it. Does that really exist? It's not clear. It does exist in our brains. It can exist in our brains, even if it can't exist in the world. And that's another thing I love about math, because we're only limited by what we can do in our brains. The world is much more limiting than that, I think. So another type of dimension is if we just think about when we go to the doctor and they take our vital statistics, which I don't like thinking about too much. So I'm all right with my blood pressure, because my blood pressure and my pulse are quite good. I never weigh quite as little as I want to, but hey, you know. So they can take your weight, your height, your blood pressure, which is 2 numbers right there, your pulse, your age. That's already 6 things. So if you were going to plot that on a graph, you would need a 6-dimensional graph. So that's 6-dimensional space right there. And then this pops up. So I'll talk about criteria instead. Every time you evaluate something according to criteria, you're thinking about different dimensions. So you can think about what restaurant you want to go to for dinner. Can you tell I'm thinking about dinner? So you can evaluate restaurants according to where they are, what kind of food they have, what the service is like, what the ambience is like, how much they cost, what time they're open. And if you tried to plot all of those different things, you'd be already thinking about that was 6 dimensions or something. And then sometimes some of those dimensions merge into each other, because maybe sometimes the ambience is related to how expensive the restaurant is in some direction or another. So actually the criteria themselves sit on a continuum, not just things that are separate. So it's kind of an infinite dimensional space of criteria. That's why I think we've been thinking in infinite dimensions all our lives. My arm seems to move only in 3 dimensions. But if you think about it like this, if you wanted to specify exactly how my arm was moving, there's one coordinate for the rotation of my wrist, and another one for how my wrist is flapping. There's another one for how my forearm is flapping, and there's another for how my forearm is rotating. There's another for how far and back my arm is, and then how much it flaps, and also the rotation of my upper arm. So I think that might have been 7 coordinates right there. So really my arm is moving in 7-dimensional space. And you meet this sometimes if you're trying to put sunscreen on your back. So if you reach down your back, like, oh, there's a microphone pack there, but you reach down your back to here, and then you get stuck. So then you have to do this and move your arm all the way around to here, and hopefully those 2 points are close enough together that you don't end up with a strip of sunburn across your back. So in 3-dimensional space, this point and this point are right next to each other. But in the 7-dimensional space of movement of my arm, they're very far apart, because I had to go all the way around here like this. And this becomes very relevant when people study robotic arms, because robotic arms have a number of hinges. And say you're using a robotic arm to do keyhole surgery, then you really need to know not just whether this thing is near here in 3-dimensional space, but it's no good if your robotic arm had to do that in order to move one little piece inside. So you really need to study the 7-dimensional space, or however many dimensional space it is, not just the 3-dimensional space. Thinking back to the criteria, if we compare ways of going on holiday, then we end up with what is really like a higher dimensional space in my work in category theory. And that's by saying, well, we could compare the different ways of getting to the place we're going. That's one dimension because we're traveling somewhere. But then we could also, we have different ways of getting there, and we can compare the different ways of getting there. So maybe we could go by train, or we could go by plane. But then we could compare the ways of comparing, right? So one, we could say train is cheaper, but it takes longer, and plane is quicker, but it's more expensive, right? So now we compare the ways of comparing, and we go, well, do we care more about spending money, or do we care more about spending time? And then we could compare the ways of comparing, and then we could compare the ways of comparing those, and compare the ways of comparing those, and that's kind of what infinite dimensional space, abstract space in category theory is. We could do this for something like comparing books as well. So sometimes people get into arguments. Well, often people get into arguments, and often the arguments are a bit pointless, because all they're doing is using different criteria to compare the same thing. So you might say, I like this book because it has a really good plot. And someone else says, yeah, but this other book has better characters. And then this person will go, yeah, but this book has a better plot. And then that one will go, yeah, but this book has better characters. This is how arguments tend to go on the internet. And unfortunately in life at the moment as well. And it'd be more sensible to compare the criteria. So you could say, well, is it better to have a better plot or better characters? And then you can say, some people I like a better plot because I like suspense, but I like better characters because I like thinking about human behavior. Then you can compare the ways of comparing. And on it goes. And you never have to stop. And the thing is that the more dimensions you use, the more nuance you have in the way that you think about the world. And so I think if we all thought more infinitely dimensional all the time, then all those arguments would become more nuanced instead of just shouting matches between different people. Maybe I'm just being an optimist that we could stop having shouting matches between people. So finally, I'd like to talk about the infinitely small. Because when I ate my Xeno cookies, maybe that last cookie, well, what was the last cookie? If I kept going forever, wasn't the last cookie 1 over infinity? Is that 0? Does that even make any sense? If 1 divided by infinity is 0, then you could multiply everything by infinity, and then what would happen? So there are ways of defining infinity to be 1 divided by 0, although it doesn't really make sense. So you have to move into a different world. And this is the thing about math, that sometimes people think it's all about getting the right answer. But really it's about exploring possible answers. And what mathematicians do in research is they dream up different worlds in which different answers make sense. And then they explore what else has to be true in that world and what the world looks like in order to make that answer make sense. And so in the world where 1 over 0 is infinity, you have some really strange looped upness in your space because it's not like normal space. And for me, that's a beautiful thing, because thinking about what a world would have to look like to create an answer is for me relevant to my life, because I can then think about what the world would have to look like in order for nobody to be afraid of mathematics, for example. That's currently a dream world, but I can work towards it by thinking of it as an imaginary world in my head, first of all. Fractals are a way that you can make things infinitely small. Fractals are where you have something that is the same as itself at a different scale. And so it's like saying you could zoom in on it and it would still keep looking like itself. So here's one that's quite famous called the Sierpinski triangle, where you take out a triangle from the middle of your triangle, and then from each of the remaining triangles, you take out a triangle, and from then you just keep doing that. So it's like a loop where you keep doing the same thing. So now I take out a triangle from each of the triangles, now I take out a triangle from each of the triangles, and I keep going, and I couldn't get any further because my computer gave up. But you could do this also with a tree. So I can start with a 2 branching for a tree, and I'm going to make a branch like that come out of each branch. And now I'm going to make a branch like that come out of each of those branches, and those, and those, and those, and those. I think that might be the end. Oh no, there's one more level. You can draw your own fractals. So I'm going to draw something resembling an Apollonian gasket now. And I think it's rather fun. And although it's quite wonky when you draw it yourself, there's something I like about drawing it myself rather than getting a computer to do it. So here's what you do. You draw a circle, and then you draw 3 circles inside the circle, touching each other. And then you fill in the biggest space you can find with the biggest circle you can fit. and then you keep going. So that instruction now repeats itself. You find the biggest space you can, and you fill it in with a circle. And it's quite therapeutic and meditative. And the interesting thing is that the thing that looks like the biggest space, you feel like you filled everything in, and then suddenly your sense of scale changes in your head. And something that previously looked like ooh, that was wonky, really small space starts looking like a really huge space that you can then fill in. And you keep going like that forever, and you have something that is quite fractal-like. And although it is very wonky, I quite like the effect of having drawn it by hand. If you look these up on the internet, there are loads and loads of beautiful pictures. Okay, maybe I'll stop now. But it's really addictive, because now this space seems enormous. Oh, this one looks enormous. Maybe you can all come and keep going in a moment. So another way you can get fractal-like thing is by pointing two mirrors at each other and taking a photo or staring down the middle, because that now goes on forever to infinity. And the reflections in the reflections in the reflections in the reflections get infinitely small. Here is a picture of me taking a picture of me, taking a picture of me, taking a picture of me forever. It's called the Drost effect, where the images of me also get infinitely small inside there. That's quite a fun thing to do. Now, you might have noticed that this whole talk has gone in a loop, because we've come back to loops, which is what I was talking about at the beginning, because fractals are made by making a loop and having something refer to itself repeatedly. And one of the things I love about math is the way that it refers to itself. Because it's abstract, you can build more math out of math all the time, which is why there's always more math for us to discover. You can't build a new bird out of birds. Birds don't work like that. You can build a sculpture of a bird out of sculptures of birds, because sculptures are abstract enough to do that. And math is abstract enough to do that. And I think that art is abstract enough to do that. So art can also refer to itself, and art can also refer to other art. And to really close this loop, I would like to show you a poem, a Basque poem, that's been translated by my same Basque friend, Amaya Gabancho, which demonstrates the way that these references make a kind of infinite self-reference that takes our thoughts off forever. So this poem refers to a painting of the fall of Icarus, but it actually refers to another poem that refers to the painting, the fall of Icarus, and the fall of Icarus refers itself to the Greek myth about Icarus. So I'm going to read you this poem. If I had to choose a poem, I'd be by W.H. Auden, the one called Musée des Beaux-Arts, which mentions Peter Bruegel's The Fall of Icarus, where Icarus is but a tiny, almost invisible figure falling into the sea. The old masters understood suffering well, says W.H. Auden. How it takes place while someone else is eating, or opening a window, or just walking dully along. Everything turns away, walks away, quite leisurely, oblivious, practically, to the disaster. The pain of someone's life almost never touches someone else. Almost no one cares for the wounds of others. The English poem references a Flemish painting. The Flemish painting, a Greek myth, and the Greek myth, who knows what? I'm by the window, waiting for Icarus to fall. I'd get a good view from here as the clouds float northward, soft, docile, without a care in the world. If he falls, his wings will hit the antennae on the roofs. There's danger in those power lines, too. If we were to join in everyone's suffering, life would be impossible. But I'm waiting for Icarus, and I'm going to help. I'll collect the pieces of his broken wings and give him shelter when he falls the way I fell, like a chicken. Thank you. Are there any questions?
So if you do have questions, we do ask that you come up to the microphones on either side of the stage.
Yeah, I was just curious if it sounds like you work with kids and teaching them interesting concepts in math, and what are the reactions when you talk to them about different infinities, uncountable versus countable
They
infinities?
scream with excitement. And that's one of the reasons that I love teaching small children, because they're much less afraid of math. They haven't learned to be afraid of math yet, and their reactions are so pure and unfettered. Whereas with older children, you get them looking nervously at each other to see whether it's okay to be excited. With the children, they just jump up and down physically, and they scream with excitement. And in fact, I talked about infinity to some 4 to 6-year-olds last year, and I came back this year to talk to them about something else. And as soon as I walked on stage, some little boy yelled, "Infinity!" He clearly remembered that about the year before. So I think that children's brains are amazing, that they can fit more things in, and they haven't learnt to have preconceptions so much about what math is. Although there was also one little boy who got really upset because I did a whole talk about infinity last year, and then this year I talked about symmetry, and this little boy got really upset afterwards and said there wasn't any numbers in it. And it's interesting because most people are kind of put off by a lot of people who are put off math are put off by numbers, and then they're relieved when I show them all the things that math is that are not numbers. But this little boy just wanted it to be about numbers. He just wanted it to be about numbers. It's not all about numbers. Hi.
Hi. In the poem, it said, "I felt like a chicken." I'm not sure what that means.
I think it means that something very sad happened to the poet. And the poet is talking about whether we should feel sad for everybody who has something sad happen to them in the world. And is saying that we can't, because then we would be overwhelmed. But we can pick one person and help them, and then that'll be okay.
So why do you think we applaud when you finish a wonderful piece of music, but not when you do these great concepts and ideas?
But you did, didn't you? I think you applauded. Thank you.
So those numbers that go on forever without repeating, how do you have certainty that they go on forever without repeating ever?
That is a great question. And it's something that we do teach I've taught it to undergraduates in first year honors math classes. And you can prove that if it can't be expressed as a fraction, then it can't ever repeat itself. Because if it did repeat itself, you could express it as a fraction. So did you follow that logic? So if it were a fraction, then it would repeat itself. And also, if it repeated itself, you could express it as a fraction, because you could take the repeating part and use that to express the fraction. So if you can prove that something is not a fraction, then you know it must never repeat itself. And it's quite easy to prove that the square root of 2 is not a fraction. It's harder to prove that pi isn't a fraction, but the square root of 2 is fairly easy. Any more questions?
If there's no more questions, then we will be having a book signing just here in the lobby, and please join me in giving another round of applause for our speaker.
Thank you.